Hello, I'm Stefan Mabry, a PhD student at the University of North Dakota. Today I'll present a survey of constraint handling in evolutionary and swarm-based optimization problems with a focus on a key gap in the literature, the lack of generation time constraint enforcement and global constraint reasoning. At a high level, optimization problems in the real world are defined by their constraints. The feasible region is often small, irregular, and shaped by dependencies between decisions rather than independent variables. Evolutionary computing and swarm intelligence methods handle this by staying flexible. They generate candidate solutions with very few assumptions about the structure. That flexibility is useful, but it comes with a trade-off. These methods do not enforce feasibility during generation, and because of that, most candidate solutions they produce are not valid. To deal with this, constraint handling is then typically added after the fact. Techniques like penalty functions, repair operators, and feasibility-based ranking are used to correct or filter out invalid solutions once they've already been generated. The issue is that this makes constraint handling reactive. The algorithm still spends time constructing and evaluating candidates that would be ruled out later. So the core problem is about when constraints are handled. Right now, constraint handling is treated as a correction step rather than something that needs to be built into the solutions that are constructed. So building on that problem, this is where the field currently sits. Most constraint handling is applied after candidate solutions are generated in both evolutionary computation as well as swarm intelligence. Techniques like penalty functions, repair operators, and those feasibility-based ranking, they dominate. So these methods ensure that the final solutions are valid, but they don't prevent invalid candidates from being created in the first place. There's some effort to move constraint handling earlier, particularly in swarm-based approaches. These methods use local feasibility checks or constructive rules during generation. They can prevent obvious violations, but they operate step by step and don't account for how early decisions limit what comes later. On the evolutionary computation side, representation level approaches like grammar guided or strongly typed genetic programming add structure to the search. But they eliminate syntactically invalid solutions, which is useful, but they stop as a structure. So constraints that depend on context, and resources, or interactions are all handled later through evaluation and repair. So across both paradigms, constraint handling is only partially integrated into the search process. It is applied after generation or enforced locally without global awareness of the solution, and then that leaves a consistent gap that there's no mechanism that enforces constraints globally during generation itself. So the research questions for the survey. So this survey is guided by these three related questions. At the center is this core issue, the constraint enforcement gap. Current methods handle those constraints, but they don't integrate them into how solutions are generated. From there, the first question is a bit descriptive. Where are the constraints actually applied in existing methods? And then to answer that, the survey maps out those constraints handlings across the optimization pipeline. And second question focuses on mechanism. What kinds of approaches are used today, whether structural, local, or algorithmic, and how do they influence feasibility? And then, together those questions frame the analysis that leads to the central point of the paper. Constraint handling exists, but it's not embedded into the generative process itself. So this slide summarizes how the survey was constructed. All papers were sourced from IEEE Explore using targeted queries focused on constraint handling and evolutionary computation and swarm intelligence. From there, titles and abstracts were screened for relevance to the research questions and then filtered by publication date to focus on recent works. Papers that passed that initial screening were then reviewed in more detail, either accepted or rejected based on constraint handling, and whether constraint handling was a central component of their methodology. And then selected papers were then analyzed and classified using a taxonomy that I will introduce later. and based on where the constraints are enforced in the optimization process. And finally, the set of papers were examined collectively to identify consistent patterns, trade-offs, and gaps in the current approaches. Here's the selection criteria. There's a small focus of these selection criteria, really focused around the top few. So the first one is relevance. Constraint handling needed to be the primary component of the method, not just like part of the application. Second, the scope. The survey was intentionally restricted to IEEE Explorer to maintain a controlled and consistent data set, and then a data set that was small enough to be evaluated. Third, recency. Only papers from 2020 to 2025 were included to reflect current approaches. And then beyond that, selection emphasized mechanism depth. Papers needed to clearly define how constraints were handled rather than relying on implicit or black box behavior. To support comparison, both evolutionary computation and swarm intelligent methods were included, even though constraint-focused work is more common in evolutionary computing. There's also a preference for structurally meaningful approaches, such as representation design or construction-based methods, since these are the most relevant to generation time enforcement. And then finally, papers were selected based on their analytical value, meaning that they could be clearly placed within this taxonomy and then contribute to the understanding of where the constraint handling occurs. So to analyze the literature, I organized the constraint handling into based on when it occurs in this optimization pipeline, instead of the algorithmic type. So at the earliest stage, pre-generation methods embed constraints directly into the representation of the model. So examples include grammar-based or encoded structures that restrict what can be generated at all. Next is the generation time enforcement, and here the constraints are applied as like candidates that are being constructed, typically through local feasibility checks or stepwise validation. Then after that, we move to decoding time methods. These approaches allow infeasible candidates to be generated, then repair and transform them into valid solutions based on before evaluation. Post-generation methods go a little bit further downstream. So they handle the infeasibility through selection, penalty functions, or filtering, allowing invalid candidates to persist, but reducing their influence. There's also evaluation stage approaches where constraints affect how solutions are scored or prioritized. They often reduce computational cost rather than preventing this infeasibility at all. And then beyond the core pipeline, there's two additional categories that appear. One is this meta-level methods that use constraints to guide algorithm configuration or selection, and then decomposition-based approaches restructure the problem itself to make constraints easier to satisfy. So this taxonomy provides a way to compare methods across both EC methods and SI methods, and more importantly, they help identify where the constraint handling is concentrated and where it's missing. So on to the results of the survey. The initial set was reduced from 54, so I found 54 papers. I removed the non-empirical studies, giving us 51 papers, and then finally, after the selection criteria that we discussed was applied, we have 16 remaining papers that were reviewed in depth and applied to the study. So each paper was then classified using the taxonomy that we just talked about, based on where this constraint handling occurs in the pipeline. A few patterns emerge immediately. So first, constraint handling is concentrated in the middle and later stages of the pipeline. So generation time and decoding time approaches appear most frequently, but post-generation methods remain a core part of the landscape, especially within the evolutionary computation side of things. Second, pre-generation approaches are relatively limited. Only a small number of papers embed constraints directly into the representation, which reinforces the idea that most methods do not restrict infeasibility at the source. Third, evolutionary computation dominates in later stages. Post-generation and evaluation-based methods are almost entirely evolutionary computation driven, reflecting a design approach that tolerates infeasibility during search and then resolves it afterwards. In contrast, swarm intelligence methods appear more often in generation time and meta level categories. So these methods are more likely to incorporate constraint handling during construction, although typically it's through local or problem specific mechanisms instead of the global mechanisms that are really needed in the evolutionary computation space. So finally, decomposition-based approaches appear in both paradigms, but they restructure the problem rather than directly enforcing the constraints during generation. So, taken together, this distribution shows that constraint handling is rarely embedded at the earliest stages of the pipeline, and instead it's applied to candidates that are already formed through localized checks during construction. So going a little bit more granularly just into the EC pattern, at the center of evolutionary computation, constraint handling is reactive. Constraints are not enforced, as solutions are constructed. They're instead, the candidates are generated first, and then feasibility is resolved afterwards. So if you look to the left, you can see why this happens. Constraint handling at the representation level does not impose some structure, but enforces during the generation itself. But enforcement during generation itself is minimal. The system is designed to explore more broadly, not to prevent these invalid solutions up front. And then on the right side, you can see the consequences of this. Infeasible candidates persist in the population and are reduced through selection pressure. Constraint handling then becomes tied to evaluation and then ranking and filtering rather than this construction methodology. So what emerges is a consistent pattern that EC does not avoid infeasibility. It's really focused on tolerating it and then correcting it later. Swarm intelligence follows a different pattern. So it doesn't fully resolve the problem though. So at the center, constraint handling is more distributed. And so instead of being deferred entirely, constraints are often incorporated during construction, which is great. That helps with some of the problems that EC methods are facing. So on the left, you can see that this shows up as local feasibility checks, though, instead of local feasibility checks and generation time enforcement. But that the localness is part of the problem that can't be applied in the EC category. So candidate solutions are then built step by step, and then each step is validated before it's committed. And so this reduces the number of infeasible solutions compared to evolutionary methods, which is great. But the limitations are pretty clear on the right side of things. The mechanisms are typically domain specific and rely on problem specific rules. More importantly, they remain local. The system validates each step, but it doesn't propagate those constraints globally across the entire solution. And this works well in swarm intelligence, but it can't really be applied in the evolutionary computation role. So while SI moves constraint handling earlier in the process, it does not fundamentally change the structure of the problem, and then it reduces infeasibility, but it doesn't eliminate the deeper inefficiency that's caused by that lack of global constraint reasoning. So these are the key research gaps, and they're not independent. They're all really intertwined. So at the center of the core issue. Constraint enforcement is not embedded in the generation process. Candidates are created first, and then infeasibility is addressed afterwards. So that leads directly to the second gap, that constraint handling is dominated by late-stage repair mechanisms. And then the algorithm spends effort exploring the regions that could have been avoided entirely. Even when constraints are applied earlier, they remain local. There's no mechanism to propagate constraint implications across the full structure, which means that early decisions are made without understanding this downstream impact. And on top of that, many of the more effective approaches rely on domain-specific rules. So they work well in narrow settings, but they don't generalize across problem types. And then finally, even the most structured approaches like grammar-based genetic programming only enforce syntax. Semantic feasibility is still deferred, which leaves the core problem unsolved. So then, taken together, these gaps point in one direction, that constraint handling needs to move up in the generative process itself, and then it needs to operate at a global level. So then, the direction suggested by the survey is to focus really on where you're spending those compute cycles on generating feasible candidates, and then reducing the number of compute cycles that you're wasting essentially on those infeasible candidates. So the first step is to move constraint enforcement into generation process. So instead of generating those candidates and correcting them later, you really focus on maintaining correct structures throughout the process. So to do that, constraint reasoning has to then become context aware. Each decision during the construction should restrict what follows, based on those global approaches instead of that local validity. So the goal is to reduce the search space by preventing infeasible candidates being generated in the first place. And that shift moves the constraint handling from the corrective process to a defining property of the search as it stands. So these are the papers that are included in the study. They're split pretty evenly between evolutionary computation and swarm intelligence methodologies. And so this is page 1 of the studies, and then page 2 of the studies. Sorry, I went back and forth. Page 1 and then this page 2. So if you have any questions, you can reach out to me on this next slide here. This is a digital presentation, so you can reach me at my email, visit me in Madison, or check out my LinkedIn page, and we can talk about any type of questions that you have. Thanks, and have a great day.